Hello guys, welcome back to CFD College. I'm Ashkan and this is the 10th video of Fluid Mechanics 1 tutorials. I hope you've enjoyed my previous videos. If so, please do not forget to subscribe the channel, to share these videos with your friends and let them enjoy these videos too. In this tutorial, which is related to dimensional analysis and similarity solution, we'll learn how to use dimensionless groups to compare the actual model and the models that we used in our laboratories. So let's jump to the first problem. We have 3 problems to solve. This is the first one, problem number 58 of chapter 7. Let's see what we have. For a certain model study involving a 1 to 5 scale model, so the scaling is 1 to 5. It means that the model is 1/5 of the prototype in size. So LM, it means that LM, the length of the model, over L, length of the prototype, is 1/5. It is known that fruit number similarity must be maintained. So first we know that we have to maintain fruit number similarity. Fruit number equals velocity over gravity times L, square root of gravity times L. It means that leave it for now. The possibility of cavitation is also to be investigated. So we have to study the cavitation. It's important because when we are dealing with cavitation, we must use absolute pressure. It is assumed that the cavitation number must be the same for the model and the prototype. Cavitation number equals PR, the pressure, minus the pressure, vapor pressure, PV, over 1/2 rho square, rho V square. Rho is the density of the fluid and velocity is the speed, the velocity of the fluid. The prototype fluid is water and 30 degrees centigrade. Model fluid is water at 70 degrees centigrade. So from table B2 you can find the properties of water at 30 degrees centigrade. Density is 995.7 kilogram per cubic meter, and vapor pressure equals 4.243 times 10 to the power 3 Pascal, and this is absolute pressure. At 70 degrees centigrade, density of the model is density of the water in the model, 977.8 kilograms per cubic meter, and vapor pressure is vapor pressure of the model is 3.116 10 to the power 4 Pascal absolute. So what should we do? If the prototype operates at an ambient pressure of 101 kilopascal, and you can see the absolute sign here, what is the required ambient pressure for the model system? So we should find PR for the model, and this is PR for the prototype. So let's start from fruit number. We know that FRM should be equal to FR. So Vm over square root of GMLM equals V over square root of G times L. Since gravity is the same, Vm over square root of Lm equals V over square root of L. So Vm over V equals the square root of Lm over L. Now for for cavitation number should be the same. So PR minus PV for the model divided by 1 over 2 rho m Vm square should be equal to PR minus PV over 1 over 2 rho V square. So PR minus PV for the model equals rho m over rho Vm square over V square PR minus PV. From fruit number similarity, we can find that Vm square over V square equals Lm over L. So we can find that PR minus PV for the model equals rho m over rho Lm over L times PR minus PV. Now it's easy, we just need to put the values. Sorry, I forgot to use this color. Okay, PR, we don't know it, minus PV for the model 3.116 10 to power 4 Pascal it's equal to 977.8 kilograms per cubic meter over 995.7 kilograms per cubic meter times 1 over 5 times 101 10 to power 3 Pascal minus 4.243 10 to power 3 Pascal. And from this you can find PR for the model is 50.2 10 to power 3 Pascal. And this is absolute pressure. This is the first problem. As you can see, it's not that difficult. Let's jump to the second problem. Problem number 63. As shown in the figure below, a noisemaker B, this is the noisemaker, is stowed behind a minesweeper A to set off enemy acoustic mines such as at sea. So this is a mine. The drag force of the noisemaker is to be studied in water tunnel at a 1/4 scale model. So as I mentioned, the length of the model should be smaller than the actual prototype. So that's what we know here. Lm over, or L or D, I don't know. Since we are working with drag, we usually use diameter. But let's move forward. So we know the scaling 1 to 4. The drag force is assumed to be a function of the speed of the ship. So here in this problem, we first have to find the dimensionless groups ourselves, and then we can solve them problem. So the drag force. Where is? Oh, okay. Drag force is a function of speed of the ship, velocity, density and viscosity of the fluid, density and viscosity, rho and mu, and the diameter of the noisemaker, and d. So if the prototype towing speed is 3 meters per second, determine the water velocity in the tunnel for the model test. And then in part B, we should find the drag force. Okay, now let's start with part A. We need to find the dimensionless groups, actually dimensionless numbers. After that, we can use similarity to find different things. So you know what to do. Making a list is the first step. 1, 2, 3, 4, and 5. We have force, unit is F. We have velocity, L over T. We have rho, mu, and d. Rho, the unit is F, T square over L to the power of 4. Mu is F, T, L square, and d is L. So m is 5, FLT, n is 3, m minus n is 2, so we have pi 1 and pi 2. And since n is 3, we should pick 3 parameters, 3 quantities. Rho, v, and d are the ones that I picked here. Rho, v, and d. So rho is gone, v is gone, and d. Now we have to find dimensionless groups. We start from F, the force, which we want to study. And here we have F, the unit. So rho has force, so I should pick and put the density here. Now I have F T square over L to power 4. Now F is cancelled, but we have time and length. So to deal with time, I should pick velocity, L over T. So I need square velocity. Now T is also gone, time I mean. And to deal with length, I need L square here. So we have D square. So this is the first dimensionless group. The second one, pi 2 equals mu. The unit is F over T, Ft over L square. So I should use rho here, F T square over L to power 4. F is gone. To deal with T, I need velocity here. Now T and T square. And I need length here. So rho v times d. So we have pi 1 and pi 2. As you know, this means that Fd over rho v square d square is a function of mu over rho v d. As you know, we can reverse the dimensionless groups. So it's equal to, for example, fn2 rho v d over mu. Why we do this? Because it is an well-known, it is a well-known dimensionless number named Reynolds number. And you can do it for the drag force, because we usually use this notation, this expression for drag force, Fd over 1 over 2 rho v square d square. This is the definition of the drag force. So it's equal to a function of rho v d over mu. So basically Cd, which is drag coefficient, is a function of Reynolds number. Now we know that we have two dimensionless groups, and using these groups we can solve the problem. For part A, we know that the speed of the prototype is 3 meters per second, and we have to determine the velocity, the water velocity in the tunnel for the model. So it means that we should use Reynolds number, because in the other dimensionless groups, we have force, and we don't know anything about the force at part A. So part A, we should have Reynolds number similarity. It means that rho m vm dm over mu m is equal to rho v d over mu. Since there is no info of the water, we assume that the condition of the water, the temperature, is the same in the model and the prototype. So rho m equals rho, and mu m equals mu. And we also know that let's move forward and then we can talk about it. So Vm dm equals Vd. So Vm equals V times d over dm. And as you know, the scaling factor is 1 to 4. It means that dm over d is 1 to 4. So d over dm equals 4. And from this we can find velocity. Vm equals velocity, which is 3 meters per second times the ratio of the length, which is 4. So the velocity of the model is 12 meters per second. For part B, if the model test of part A, so we know the velocity, produced a model drag of 900 Newton, determine the drag expected on the prototype. So now we know that the drag force of the model equals 900 Newton, and we want to find Fd. So this is part B. Since we have Reynolds number similarity, it means that actually, since the Reynolds number for the model and prototype are the same, it means that the drag coefficient for the model should be equal to the drag coefficient of the prototype. This is the benefit of this relation. the dimensional analysis. So if the Reynolds number for the model, for two models actually, are the same, it means that the drag force should be the same, because the drag force is only a function of Reynolds number. Okay, so from this we know that FdM over 1 over 2 rho m Vm square dm square is equal to Fd over 1 over 2 rho v square d square. And from this we can find that Fd, and we know that the densities are the same. So Fd equals Fdm times V over Vm square times d over dm square. It's equal to 900 newtons times V over Vm, 3 meters per second, over 12 meters per second, times d over d, which is 4 square. This is another square. Okay. So as you know, as you can see, Fd is also 900 Newton for the actual prototype. So as we can see, it was a bit tricky. You need to find the dimensionless groups yourself in some problems. So, and after that you can use the similarity solution. This is the third problem. Problem number 65. The drag characteristics of an airplane are to be determined by model test in a wind tunnel operated at an absolute pressure of 1,300 kilopascals. So this is the absolute pressure. And okay, if the prototype is to cruise in a standard air at 385 kilometers per hour, so we know velocity is 385 kilometers per hour, which is equal to 107 meters per second. You should divide it by 3.6, and the corresponding speed of the model is not to differ by more than 20% from this. So Vm equals 1 plus or minus 0.2 times velocity. And so we also have the pressure for the model, which is 1,300 kilopascals absolute. What range of length scales? So now we should find the scaling may be used. I missed this. Compressibility effects may be ignored. Okay. What range of length scales may be used if Reynolds number similarity is to be maintained? As you know, Reynolds number equals rho v d or rho vl. It doesn't matter. The characteristic length we have over mu is to be maintained. Assume the viscosity of air is unaffected by pressure. It means that mu equals mu m. And the temperature of air in the tunnel is equal to the temperature of air in which the airplane will fly. So T equals Tm. Since we have air, we are working with air, we should use, I think, ideal gas law, which tells us that P equals rho RT. So we have Reynolds number similarity. It means that Reynolds equals Reynolds of the model equals Reynolds number. So rho m Vm Lm over mu m equals rho V L over mu. And we know that mu m is equal to mu, so these are gone. So Lm over L, which we have to find, equals rho over rho m times velocity over Vm. So we have the ratio of the velocities, but we don't know anything about the ratio of densities, but we have a hint here. T equals Tm. It means that we should use ideal gas law. So we know that R, the universal gas constant, I think, and T are the same for both. So as you know, it means that P equals rho R T. It means that P over rho equals R T. So P over rho is constant because T and R are constants. It means that Pm over rho m should be equal to P over rho, and it means that Pm over P equals rho over rho m. Now we can put this in the equation number 1. So Lm over L equals P over Pm times V over Vm equals 101 kilopascal and 1300 kilopascals. Both are absolute pressures, times V over 1 plus or minus 0.2 times V. From this, you can find Lm over L. So we have two limits, two numbers. Lm over L equals 0.0647, or if you use the minus, the negative sign, it's equal to 0.0971. These are the scalings that we wanted to find, the range of length scale. So this is the minimum and this is the maximum. That's it. This is the end of this video. I hope you've enjoyed it. It's not difficult, actually. This chapter is easy for you to solve the problems. In the end, if you have any comment, you can write it in the comment section below. Thank you for watching these videos. Don't forget to subscribe and share these videos with your friends. And until the next video, take care of yourselves. Bye bye.